Okay, we are live. Hello again. Uh, Hopefully this will be the last of this series of videos. Yeah, my name is Christian and I'm going to guide you to actually run a program inside of this mess that we did. So I'm going to go do a quick rundown. I actually updated the idea to the latest version, but sorry, this is not the project. Holy shit, sorry. It's the what's the effect console? Oh, okay. See. Sorry, I handle a lot of projects here, so not used to. So I'm going to do you a quick rundown of whatever it happened the last time. So yes, we implemented a circuit. Well, as system generation using chipyard, where we actually integrate an UART, a GPIO, and a ROM that is named my boot ROM. Yeah, that's about it. And I don't get why it gets now. It didn't actually did it like accordingly. This happens when I actually do this. Chips Alliance is not there. Nothing is here. Well, we are not interested right now in this, in doing hardware right now. Right now we are going to go into the software. So as you can see, there's going to be a UART in this address, there's going to be a GPIO on this address, and there's going to be a ROM on this address. And we haven't put anything on the ROM. So let me tell you why. The reason is that we actually, in the make files, let me actually guide you there. Where's the RISC-V? RISC-V console. So let me guide you there. When we did the FPGA, we added a rule here about the ROM, and the ROM will do the Python of this script that is named the VLSI boot ROM, that will create a black box for that ROM that we created before. This ROM. If you are maybe skeptical about the implementation of that, it will be eventually inside of this Verilog file, the top file. So if you search inside of here for the name that you put into this ROM, that is named my boot ROM, eventually it will pop up. I'm going to search it right now. Let me search very quick. Yeah, it's here. So there is actually a black box. That means that that as you can see, this is the only match of the system, and it gets instantiated using this TLMax ROM, and this is just a regular tile link, and that tile link will be connected to the system, whatever is in there. Not much is happening there. It's just remember that tile link is just an address channel that actually puts the address and stuff and retrieves the data through the data. So it's just a converter for this one. But we're interested in this ROM right now, and this ROM gets created by that script, and we put it inside of a file named, I don't remember the name actually right now. We put it in a ROM file. Yes, name it whatever is in ROM file. Whatever is named the long file name .rom.v. So if we open here and search for that file that is here, it creates this. Very straightforward, because we put a dummy X file, the X file being here, where we just put zeros. and these zeros are going to be put here for each of the address. That's pretty much it. Now, depending on how do you actually integrate this, for example, this one, I created this one. I mean, that was based on the other one that was there. But the original one that is in Rocket chip, it will create you this very ROM, but it will create it as a RAM for with an initial, and that is compatible with some of the FPGA software, but not all of them. So maybe it will have some problems to actually put inside the memory. And according to my experience, actually sometimes it gets the memory blank because it just ignores the initial, literally an initial where it loads this X file and put it inside of the memory, and this is a regular RAM memory. So that's why I consider that and the approach actually a little flawed, but it's not too much. So what we're going to do here is to actually put a program inside here. So as you can see, we need an hexadecimal file, and we put that hexadecimal file whatever we want. Yes, there are supposed to be boot rooms for that. I mean, there are literal boot rooms already compiled and ready to go, but that doesn't explain how they work. And we are going to do a pretty simple one without any kind of additional stuff put inside of whatever. No, just a regular bootloader where we are going to blink a LED. So let's get started. First of all, we are going to create in our folder. Well, we already have it, a software one. So we have the RISC ISA and the RISC-V test, but we are going to put a new one that is the name it bootloader or something like that. Yeah, I am not that creative. And we need here like a little file. So I'm going to put here bootloader.s. No, sorry. Better to put start.s. .s dot no. Sorry. Why did I do that? I have the sorry for the people that are in love with the terminal. Sometimes I go too graphical. Okay, I have our start, and we have and we need to have a link.ld. And that's pretty much it. Those are the two programs that we need. Quick warning: you will need to compile your toolchain at this point. So if you are curious about how to do it, it's actually pretty simple. You just go to RISC-V toolchain, the new toolchain, I think. Yes. There are the instructions here. But you're interested in the one that actually goes for multilib. Why? Because as you maybe have noticed, the multilib provides both 32 and 64 bits, and they're ready to go. And this will take at least maybe half an hour, or if your computer is too slow, maybe 2 hours. It depends, but it's not that difficult. I mean, it's more. It's going to take longer the actual download of the stuff. So and yes, you need to put this here. A quick order warning: these people doesn't actually put in them in their instructions. But you need to make this folder accessible for or proprietary for the guy that is actually doing the compilation. I explained. So you need to create this folder. For example, you go to the console, and you do sudo engineer this thing. Obviously you put up your password, but this if I try to do anything, sorry, I'm going to put this a little bigger. Okay, if you try to touch any file inside of it, you won't be able to. So RISC-V maybe no, it's not going to delete me because I don't have the permissions to do so. And a typical mistake that the people do when they compile their toolchain is to compile with super user, because most of the problems actually comes that you don't have permissions to actually write there. And this repository assumes that the user that actually doing the compilation has the actual permits to do so. So you won't be able to do it unless you own this folder or you make accessible for writing of that folder. I recommend the first one, so sudo own and you put your user. For my case is this one, and I'm going to put opt RISC-V. That's pretty much it. And now if I do this, I will be able to and you can remove as well. So there's that. So it's not stated here, but once you run this, it will start to write every result of the compilation, and the compilation will have the GCC, the bin utils, and the GDB, and all the libraries that I am aware that maybe that is new lib, and everything will be copied there. And if you don't have the permits, you will have a bad time. Again, for the guy that actually knows how to handle this, you will be able. It's just that I hate people that actually do compilation with sudo. You want to damage your system with that, so that is a no. Anyway, so yeah, we are going to start doing this start.s. Maybe I need to do also a makefile. So touch makefile, and maybe also touch for a git ignore, because I don't know if you are going to ignore some generated stuff here. So let's start with our program. So everything is starts with the start. So you need to make this as the entry point of the system. So if you put it in the first thing in the start.s, it will be your first instruction, so you don't have to worry too much about it. But I need to do something like declare that this section is the section init, or the section text. Why is that? We will see you in a moment when we are integrating this link.ld. We haven't started yet, and we are going to make this symbol global start. That's pretty much the configurations to the compiler that you need to do. Everything that starts with a point is a compilation comment. So that means that there are not actual instructions of the RISC-V. I get a lot of people that actually confuse those two, and they are not. They are only commands that you put to the compiler to actually have some configuration. So we are telling the section that will be from now on will be that the init stuff, and the global will be start, and this will be the start. So I'm going to do underscore start. Actually, I don't know why they use underscore start. It can be start or underscore start. It doesn't matter. And we are going to put some instructions here. Now, there are some stuff that I don't know how that work actually, like the CFI. Let me tell you actually here. When you go to, for example, I'm very inspired to whatever is inside in Freedom, the ESDK. This is the first SDK that Sci-Fi did, And we are not going to look at the latest version. We are going to look at the old version. Wow, there's a lot of stuff here. 1.0, because it's easier to read. So if we go to, for example, to the hi-fi one, this applies to every one of them. You will appreciate that actually they do some kind of stuff. Look, I even had bad this global. It's global. It's global. I don't even know the name. You need to actually know whatever is there. And this is what I'm doing. I know what it does, but I don't know the reason why. If you remove these two, the return address will be assumed that exists. So in order to understand that, you need to understand how functions work, and that is a long story. But the long story short is that when you call a function, it will use always the array as the reference for returning. And it's assumed that the return address is in an initial state at that point. Same for the global pointer. Why is that? For reference because this is a compiler for C. It uses both array and GP and the program counter as well to actually deduce all the address offsets. And maybe if you're interested in RISC-V, I mean, you have to be interested in RISC-V for at this point. That if you for example, for the calls, if you do a call that is more than 4 kilobytes away, it needs another type of instruction that is not the instruction that you have before, for jumping, I mean. So they use these registers to actually do the actual pointing. Again, those are perks that are inside of the compiler. Whoever did the compiler is the one that actually handles that. And because we are doing this in GCC, every care about this needs to be done to actually initialize, because the compiler assumes that everything is done at this point. Why? Because these executables are made compatible for Linux, and they are not intended to actually run in a first stage bootloader. So that's why you need to take a lot of care. It's because we are running actually in a very secluded way, to actually limited way to do it. So we need to do these options, this CFI, to actually set the global pointer, set the stack pointer, and that kind of stuff. So I'm going to literally copy this because it's necessary. It needs to be always in the beginning of anything. That's pretty much it. I'm using spaces. I'm going to color this a little. I'm going to put a little comment here, comment to be processed as a C. So we declare that the array is undefined. We do the push and no relax. This is for setting the actual value of the global pointer. And the compiler from now on will know where is the global pointer instead of actually assuming where it is. And we need to finish this thing with the CFI and proc, or otherwise it won't be able. Again, I am not sure what the CFI proc does by itself. I know what it does if you don't put it. That is just mess with the location of the GP and the ESP. That's pretty much it. So don't worry too much about this, the value of this or the value of this. you know, this load address, this will use like it will try to use AUEPC and maybe add and maybe add ADI. Actually, this is for actually loading constants, but using the PC as a relevance. That's what literally means this AUEPC. The Louis is the one that actually just loads the constants plane. So that's why there is a pseudo instruction that is named LA and other that is named LA and LI. Yes, LA and LI. So those two are the first instructions that you need to put, and from here you can put whatever you want. So we are ready. We are finally ready to go. So we are going. I am going to use the address A0, but actually I need to actually put the to do the frame stack before actually running this. This is for compatibility, for compatibility reasons. You don't need to actually put it, but I'm going to put it because I am a good boy. I need to do everything good. So I'm going to tell you what this does. It just puts as you see, it puts the array to be in this very address, and that will trigger the whenever we are actually going to debug. If we are going to debug this system, the stack will stop here, and this is a way to actually tell to the debugger that, hey, the stack ends here. Don't go any further. Otherwise, the GDB will say that actually the stack pointer is actually the stack is totally diminished. Totally corrupt, and it will display a warning there, but it's not a big deal. Anyway, I'm going to load this in A0. I actually promised you to actually write something into the GPIO. So the GPIO is actually in this address, so I'm going to just load it here. And the question is, how do you know where to look at, what to do with this? The answer is very simple. I mean, you need to know the offsets of the GPIO. If you are not sure about those, you can always go to the Sci-Fi site and actually extract it from there. So there we have a documentation about here. I don't remember where. Software boards, custom silicon documentation, I think is here. I mean, there's a lot of Coreplex that they have, chips and boards, FPGA and tools and stuff. We need the manual maybe for I mean, the actual peripheral haven't changed it, so you can look any of them and will be okay, as long as they have a GPIO. It's just that these manuals will have the stuff, the stuff that they actually generated in this kind of systems. So we need to see where's the table of contents. Okay, the GPIO here. So it works like this, and the offsets are like that. And this is the same because remember, if you see good, we put the Sci-Fi blocks here, and so that means that this is going to be the memory map about this. So whatever. I'm going to put it in the side. I'm going to put this other in the other side and try to blink this thing. So I'm going to put an infinite 4 around here, so maybe something like that. I'm going to put also an infinite jump here. One again. Yes, and jump to 1B. So if you want a mnemotechnic for this, 1B, 1 before. And if you only put 1, it's because it's 1 after. So that's how it works. So I'm going to put also 1 here, but here I'm going to put the stuff. So I'm going to blink all the LEDs, whatever is there. I know that in the output enable and the output value we can put whatever. But that whatever needs to be in pair of whatever GPIOs are there. But it won't matter if you write one where it's supposed to be nothing. You just do it. It will just ignore whatever don't write, that is not able to write. So that will be able to blink all the LEDs. So let me tell you how that is done. So I'm going to load A1 with all the things in F, and I'm going to enable all the GPIOs. So I'm going to do an SW of A1 to 0 of A0. No, not because I need to do it in the output enable. So that will be 0x8. I'm going to put a little comment here that is put all enables in 1. Very straightforward. Then you actually do it like this, and then we are going to blink this. How we are going to blink this? We can blink it as fast as we can, and this is going to be a very simple program that actually saves in the C address of this A0 the value of whatever is A1, but we need to put it in 1 and in 0. So I will do it like this. So I can do an XOR I, that is A1 of A1 again, and -1. Okay, quick explanation about this. XOR I, so is XOR immediate. That means that we will do a XOR. We will do a XOR against A1, and we will store it again in A1. And the -1 will actually translate. Remember, to complement is actually in whatever bits they have. I think there are 12, so something like this. So 12 F. I mean, this is the constant. This is the IMM. But remember that this is arithmetic. That means that the sign will be replicated in the rest of the stuff. So actually, we are doing virtually a XOR with 0 is F totally everything in 1. And if you do a XOR with F's, it's the same as not. Now I don't know if they have a pseudo instruction that actually is named not, but I am not going to dig into that because I already know that this works. And for now, we are going to do it like this, and this is the program. So as I told you, it's very simple. So you need an initialization stage to put this global pointer, to put the stack pointer. Then from the stack pointer, you put the return address in this very address, in this whatever this instruction is referenced to. It puts the SP it shifts down a little the stack pointer, and depending of the X length, of the stuff, it will SW the RA to 8 or to 8 of the SP, or do it with SD. And this safe double word for you there. From here we will load the we will just load the offset of the GPIO to this register to actually have it ready there. As for this one, we also load this constant. So that constant that is all in ones, we will put all the tables in one. Then we put everything there, and not all the enabled. Sorry, I put all the GPIOs in A1 state, and negate everything. Then do an infinite loop around here. If for some reason goes out of this loop, it will catch this loop, and this is an infinite loop, so it won't be able to execute whatever garbage is beyond this point. So it's okay. Okay, so we are ready to go, and we need a link script. I'm not going to bother too much with the link script, but because we are going to take one that is already there. Again, you don't have to know everything about this. The people that actually are interested inside of the compilation process is the one that actually needs to be aware about this. But we can just take any LDS, and we can make it our own. So I'm going to copy this one. I know that this one works, but this one is made for systems that have a flash and a RAM. So, and the flash contains everything, even the variables, whatever. Yes. So I'm going to rename this flash to ROM, maybe. Holy shit. H. In which case, an entire word to ROM, maybe. And we know by effect that this is not in this address. We are in address 10,000, and the length of this will be like I don't know, maybe 2 kilobytes only. I'm going to start with 2 kilobytes for now. If you need more, you put it inside of the system as well. So how much is by default? Sorry, I don't have the access for that. But let's assume that is 2K. I think it's less. Doesn't matter for now. Okay, so we're going to define the stack size. So this is a script. They call it the linker script. As a script, you can define any kind of variables and stuff, and this will tell to the compiler, actually not to the compiler, actually to the linker, where the hell are you going to put it inside of the whole memory. So if you want certain section to be in this certain way, you need to put it inside there. This will do the trick. So as you can see, the one that we are most interested in is init, and init is put it in ROM at ROM in ROM, so it will be definitely in the address 10,000. Now this particular linker script will also put the variables in this address, but remember that the only source of data is the ROM. So for example, they have here a little, if you go down, the data section that actually holds all the variables and stuff for the C file, or maybe also the assembly file, if you put it there, it will put it in the RAM, but the actual location of the data, like the value that represents, is stored in ROM. and we tag this as RAM init. That is a PHDRS. It's just you can read this as references to anything. And they have a special program to actually load those kind of stuff, but we didn't put it here. I'm going to put it as a to-do actually. Or for C variables. That is just copying whatever is inside of this tag. That is actually this tag here, that is data and e-data, and copy it to the memory. That's pretty much it. So it's like an analyzation stage to actually have that stuff ready. And that's pretty much it. That's all we need. You can read this maybe a little if you are curious about what everything does here. You don't have to. You just need to actually understand it a little and understand that init needs to be in the beginning, and we put everything in init here. And the start start point needs to be named start with underscore. Yes, that's it. Now we can proceed to do the make file. So I'm going to put here some rules. So all being I'm going to create an elf, a bean, and an x file. And we are going to put also a clean one, and we have put everything here without using spaces. We are going to put the CC that actually is RISC-V 564 unknown Linux. Sorry, what was the name again? Unknown elf, sorry. Unknown elf. I always forgot. And you need pretty much it, the clean, and you need to do phony. You need to do phony the clean, so it can actually run every time. Okay, in the clean stage, I'm going to put every elf and every O and every D maybe, because maybe this will create D files. Okay, all. If we are going to do all, we are going to take a name. So all will be the bootloader dot x maybe. I don't know. So to do the elf is actually do the bootloader dot elf. Same for the bootloader dot bin dot x bootloader dot x. For every dot o is actually comes from a C. And we need to put that a little of C flags here. The C flags actually are the arch that you want to use, RV32 iMac for this one, and with a MABI of ELP32, I think. Those are the only flags. And now the LD flags needs to be done like. We need to do some stuff there that I don't remember. Sorry, I don't remember exactly which ones you need to put it inside. Again, you don't need to know everything. Okay, they put the linker script and the no star files and the nano specs. Okay. That's everything in the LD flags. Yes, that's everything. So LD flags, you need to put the linker script. So the linker script, you need to assign it before. It's actually link.ld. like I did, like we have it before. Link LD, no star files, and library. This for allowing library stuff. Yeah, we don't need it. And the specs. That's the nano specs. What about the C flags? They put the G for debugging. Okay, we can put the debugging. The MA arch, the MABI, and the model. Okay, the memory model. Yes. I don't remember what is this. But if they put it, we are going to put it as well. It's not laziness. It's just that I don't know how that exactly works. But with this works. Okay. So let's do the rules. So for the elf, we need actually we need start.o. We have a start.o. Whatever is above this line, we will put it there. So for the CC, whatever is up, and O to the output to the L file with the LD flags. So, and what is this? This is named the linker step. So whatever is compiled, like this is start.o that we are going to compile, we are going to put everything here, and you can put every file here, and everything will be inside of this bootloader.elf with whatever flags we have. In this stage is where the linker script is used. So whatever it gets compiled to, it will be integrated all inside of the elf file. Now for the bin file, we are going to put the bin file. So for the bin file, we need to have the yes, this is GCC, elf GCC. Actually, we need like a RISC-V stuff here. No, RISC-V prefix, maybe. The prefix is this one, and we are going to put this here. Sorry, this one. DCC, and we are going to put here for the OBJ dump. Was copy. No, I think it's already dump. So to actually, for doing that bin from the elf, you need to put the obj dump in the format that you want to do. So the format is, you need to do output binary. I think we have it here. No, I don't have it here. Maybe the make file of this. Wait. Why is not here? Indeed, why is not there? Even the linker script is there. The LD flags are there, and the target. Now I remember why. No. It's because they used the bare executable, the L file, to actually do it. We need to do it in the old way. So OBJ dump. Where do we actually get the OBJ dump? Maybe one of my private stuff. Maybe. Okay, no. Maybe from the repository of what we already have. The TE hardware, maybe. I think I did do something for that inside here. Ah, yes. Okay, it's very simple. You just need to do this. Again, you can find this eventually in Google. It's just that I don't know where to look at. And this will create the bin file from the L file. Now for the X. The X file is this command here. I know that you can actually read all the documentation you want about the OD, but this will give you a clean X file from the stuff. Or you can do your Python like they did in PQRB. Whatever flow you want. So bootloader.x. For this we need the bin file. So whatever is binary here, we put it as an hexadecimal plain file, and this is this command. Yes, that's pretty much it. Now we need to do the start.o or the start.c. So for compiling that kind of stuff, I actually have the rule here. I don't know if I have the rule here. No, I don't have the rule here. That is inside Freedom. C flags and includes and stuff. So it's something like this with the C flags. I have the C flags here. Yes. We don't need includes because we don't have them. CO, the output file is this one and the input is this one. The C is for compiling. Perfect. And we are ready. So we can test this make file. Okay. So make n. What the hell? It didn't put anything here. What happened to the C flags? Okay. Maybe if we put it like this, it will work. Maybe we add it? No. Holy shit, what happened? How they put the C flags here? They use an addition here. I mean, it comes from an original make file, but or something like that. I wonder, but I did this wrong. It's just that it does this does whatever he wants. What the hell, actually? Hmm. 421. Okay. Oh, it's the latest one, I think. But the LD flags. You know what is happening is that it is creating the dependency by merely by itself. That's the problem. So I need to maybe do it before. No. Okay. Time to search for the Google. So maybe if I put it inside of quotes, it will fix it. No. I put it wrong, but it's the same one. And CC works. Why LD flags not? Okay, implicit. What if we don't put this rule at all? Yes, that's what I thinking is happening. Yes. But why? I mean, they have here the ASM objects or the C objects with the headers or whatever. But I just don't get it. So what is happening is that instead using this rule automatically, is not letting me choose for the rule. Freaking makefile. This is the stuff that actually you get for actually using this. So suffix rules. Everywhere at the percentage is okay. Look, I am looking at the documentation of GNU Makefile, and they explicitly say this, and I have it like that. So I need to have a space or something. Let's do with the space. I don't know. Ah, okay. I know why. Because I'm a stupid. You need to have one for C and one for O. Actually, the command is the same for both of them. Now it will do it. Perfect. Sorry for that. Sorry, very sorry for that. It's actually very easy to do. So if I do make, it will run and start to run errors, because that's if there's no errors, there's no way that we are actually advancing. The ABI is not compatible with the RB32 by Mac. Why? It's ILP, no? I mean, maybe we can check it with the settings. RB32 iMac with ILP32. They changed it again, right? Which one of which version of GCC? Maybe it's 10.2. They changed it again. What the hell? They changed the options for the C flags. What the hell is wrong with these people? GCC 10.2 RISC-V whatever Abby. What the hell? And doesn't put everything. Maybe the GCC can tell us. The GCC can tell us. Maybe. Please tell me. They hurt me bad. And that's why you spend 2 or 3 hours doing this. Because some option that it was supposed to be a what? Something that it was concept from everyone to be like that, and a standard to be like that, now is not working. Because somebody decided in this version to change it, and you don't have to, you don't know what to do unless you are subscribed to that and actually do it. What the hell? And look, even the official one says that ELP is 32-bit for SOT. Yes, it's okay. So what the hell? Unless this GCC is not compatible with that. By the way, which one version are you using? Which RISC-V 64 unknown ELF GCC? So it's a G64 GC. But I was warned that actually this one is multi-level. So maybe this one in specific is not multi-level. Maybe I did actually screw up my own warning, and I ended up doing the other one. So I am going to use the old one. So I'm going to do the export path to this path, to the previous path, but I'm going to prioritize the OPT RISC-V 64 GC.old bin. And now let's see if it works again. The AVI is not compatible. What is version 9? And this seems like only is compatible with LFLAG 64. What the hell? Wait, they already compiled? Make clean. Okay. MRF. And the LD flags, I think we actually forgot to actually put this as well. Wait, what? Why is running for elf? Alas. And boulevard.elf. OBG dump. Yes, it's okay. So what the hell? How did I use the OBG dump here? Because it's OBG copy, no OBG dump. I'm useless. Copy. and copy here. Perfect. Now we can do it again. Perfect. Make clean, make. Perfect. So it's compatible right now. Yes, it seems like the version that I compiled to new, the latest one that I did, it was not multi-lib, so it didn't support this, but can be also that it no longer supports the ABI, which is bad. Anyway, so with this we have the bootloader.x and this thing here, and we can put it to the we can literally copy this to there, or we can actually make it dependent when we build the hardware. So it will need always a bit a DOM file. So we are not going to do it like this anymore. Maybe the sim there, the base there. We're going to do a software there. No, bootloader there. No. First software. The software is going to be the actual one that actually had in base there, but with what? With software. And the bootloader is going to be there as well. The bootloader there is going to be the software with bootloader. So this will be in the bootloader, name it bootloader.x. So the rule for doing this bootloader.x in this hardware file is going to be sorry, I need to put this in a space without spaces, and this will be make C make C and bootloader there, and the bootloader, the X file. Pretty much that's it. Okay, that should be enough. So the next time we run in the FPGA, it will be like that. So we can sit finally and see if it works. FPGA and the ULX3S. Make clean, make. I'm going to, for a good measure, I'm going to run that to remove the dummy. X. Make. I think it's make PNR. No. For program? No, I mean we can do to pack, up to pack, I think, pack. And we can see if it works. Finally. I mean, I am almost certainly sure that it's going to fail. It always fails. It doesn't fail. We are not doing this right. If it works at first try, it will actually do okay. I'm going to sum up in the meantime what we did. So we actually make some stuff there. Sorry. Come on. Okay. So we did the start.s that will be contain this program here that will just blink a LED very quickly. The link file that contains something that made sci-fi that will organize the sections whatever they want to be in the memory in the moment that this bootloader gets created. So the ROM will be in the address 10,000 and the RAM will be in the 80 million like it's supposed to be. And this is pretty much it. The stuff that I'm going to do. Everything is originally going to be in the ROM, but if something RAM is necessary, it will put it accordingly regarding the compiler. Now, they make file that actually gives you a little headache. In the order, you will need to compile the S files, the assembly files. Then if you have also C files, we will compile it in the same format. Then for the bootloader, we put every .o that we need, not the .c or anything, no, because we need the compiled version of that. that will put this command will link all together, and you need to put the start always at the beginning. I will put all the program inside of an ELF file. Now, for generating a binary from the ELF, you need to do obj copy. And now, from the binary file that you created, you can create the X file that will create that beautiful file that creates right here. That is this one. And those are the instructions that will be inside of the ROM file, literally. And yeah, that's pretty much it. Okay, it failed. Why? There's still references to dummy.else. I think I screwed up. Oh yes, they are. Sorry, my bad. So let's do it again. Ah, sorry. Okay. It's always good to see the work from far away. I mean, not literally. I'm going to do far away here, but I mean, look what we have done in the last stuff. I mean, we are just going to blink a LED. That is the punniest thing that you actually do. It's totally awful. But no. Actually, it's a very good, because in order to blink the LED, you need to do all the system, and the whole system will run whatever program you like. So in order to do that, we needed to do the simulation step. Those steps are from Chipyard. The Chipyard will do it here, then run this whatever, and put the DTS and your FreeRTL code. Then for the FreeRTL code, it will create the Verilog file, and the Verilog file you can put it in the FPGA flow. The FPGA flow will do a bit file and we'll put there. And as for the program that is going to run for now, is stored in ROM. So whatever you change your program is going to be a mess, because you need to recompile every time the FPGA. Now there are easier ways to do it, like if we put this with or we use the flash component here, we can be able to read and write to that one and start the program from there. We can do a little better. That's my point. And that's pretty much it. But for now, it's going to be just inside of the ROM. It's going to be a mess. It's going to take. It's always going to take a while, and my fan, it will be always going to be noisy as hell, because this is a laptop. It is not a quote-unquote gaming laptop. Okay, now it's there. Now we can confirm from here. Then actually the actual ROM file goes inside, and you can see that yes, it got there. You compare this with this, similar, the same one. Pretty neat. Hopefully it will work. I have faith that maybe it will work. We'll do the optimization, we'll do other stuff. This is still Joseph. We'll put in the loops, and we'll put in whatever. Hopefully it will work. I am not sure. After the whole open source stuff, I don't know if it's going to work. I honestly don't think so. I mean, maybe. And the resets, maybe we didn't have enough care with the resets. Maybe the system is going to be always resetted, and the only way to actually test it is to actually have it run in hardware, in software, maybe in simulations. So maybe we need to run this very stuff in the simulation that we had before. But if it doesn't work right now, I will do a follow-up video actually doing it in Verilog. This is intended to be the last part of this RISC-V series, so it won't be any more. That's my point. So regardless if it works and it doesn't work, that has been an experience, and you know how to generate stuff and put it inside of an FPGA. This guy's an open one. For the icebreaker, I mean, the icebreaker is much smaller. That is the same one that is the tiny FPGA, the AX or the VX series. Those two are also too tiny. So because they are too tiny, this kind of system is not going to fit. In order to fit, you need to put it even smaller. To do it smaller, you need to change the settings, everything about this. And we are using L2. I didn't realize this. We are using L2 cache in a microcontroller. That is so useless. We can put the cache currents to be a broadcast. That means that it won't be an L2 there. Oh, I screwed up there. My bad. What I needed to do something like quick. I remember. I don't remember. It's already 1 month. 1 month, my God. More than 1 month. This is the 5th week of this series. Iteration, iterations. After this, I will see if this tiny thing can actually run Linux. I will put a Rocket Core with GC, and we'll put a Linux inside. I will write something for tutorial for that, and see if it truly is, because this FPGA is advertised to run Linux. I don't know which kind of Linux. I haven't seen in the examples, but it doesn't matter. It seems like for the size of the FPGA, you can actually fit a system that runs Linux there. Or maybe it doesn't run the Linux from Rocket. It will use maybe an ARM core or an ARC core, or can be also the VEX RISC-V one. Not sure. There's quite different ways to do it. Simulated annealing? What the hell? Now that is a name I haven't heard in a while. That's for I thought that simulated annealing was for floor plan, not for placement. I mean, you can use it for placement as well. I mean, floor plan is just another wrong way to say placement. But do it in FPGA? the placement, some simulated an alien, Psycho Mantis. And now it's routing. 74,000 arcs. What the hell? It's because we included L2. The L2 was not, seriously was not supposed to be there. The hell, man. I wonder if it will be capable of. I'm not sure. I think it's not. I totally forgot to bring my debugger to actually do it, because we put this in a debugger, no? I mean, if you check the code in the ULX3S, you saw here that actually this we put the TDI to the GP 0, 1, 2, and 3. So you can connect the JTAG to there, and using OpenOCD you can connect to the debugger. At least that is supposed to work. Now it doesn't use the clock gating that was supposed to be there, because remember we actually ditched that one because it was not compilable. So there. I wonder what is happening with this. I mean, maybe if we re-import stuff. What happened here? Maybe if we recompile this one, maybe re-import this one, it will work. So this will always create an idea folder. You can just remove it and then import it again. It works now or not? We haven't indexed it yet. Okay, it's done. Let's see what we ended up doing here. If it doesn't do it, we need to debug it. If it does it, we have succeeded. So make prod. Program. And I'll find the JTAG table because we need to do it with sudo. And programming, and fail. Come on. Wow, it worked. They are blinking so fast. But in the original one, remember that these ones were totally off. Wow, this worked. Even I am surprised that, I mean, that has to be a speedrun. I managed to do a full implementation of the chip jar in just 7 hours. I mean, realistic 7 hours. I mean, I can be a whole day and implement this with software included. What the hell? And now you have the way to do it by yourselves. So that's a plus. And this worked. Wow, everything is worked. Today's a good day. So we can finally check that the blinking of the processor is totally done. I mean, to do it properly, you need to put a four there, no? I mean, between this point here, sorry, not this one, this one. So for the start S, this one, maybe a little 4 here that we actually delay a little the stuff. Look at it. It's so cute. And all the LEDs are doing their stuff. I mean, they're blinking so fast. And the I think it's the processor is the FPGA is 25 megahertz. Let's assume that actually it takes two clock cycles to actually execute an instruction. That means divided by 4. No, 2. So no, but actually writing to the GPIO takes longer. It's at least 1 megahertz maybe, or yeah, or 900 kilohertz that is blinking. So obviously the it's not doing anything there. It just put it all on. I wonder. Yes, this was the reset that we actually assigned. If we do the reset, it will turn on and off. Wow. You wanted to do it. The blinking is lower. You need to put a way to stay here. Something like a counter or something. I don't know. Maybe something like this. I am not sure, but maybe it will work something like this, like li a2 of maybe some random number, maybe 10,000, then 100, sorry, 100,000. Then put a second label here. Then BNE, no, be he greater or equal. No. Less than. No, be branch if not 0. Branch if not 0. BNC? No. Be not equal. BNE. Not equal to 0. To 0 of A2. And bring to the B to B, and maybe do A2 like add A2 to A2 0 minus 1. Something like that should be working. For doing it a little slower to blink. So and it will create a little different this thing. Yes, it will add some instructions, then put it inside of the ROM file, and we'll do something different. That's pretty much it. Wow, it was a journey. Thank you very much for being here. I will do a follow-up about this, maybe in a video, maybe I don't, about putting Linux inside of this, or maybe the process to actually put the Linux there. I mean, you need to take a little more of care about the bootloaders and where to put the SBI and where to put the Linux and all the stuff. Then you put everything in alignment. You need to align the planets, because this is everything about aligning the planets. But I'm happy with this result. Yes. Okay. So see you next time, I suppose. Thank you very much for watching.